Okay. Hi everyone. This is Sachin Kumar, a PhD scholar from my Department of Material Science and Engineering, Indian Institute of Technology, Kanpur, working under the supervision of Kaustubh Kulkarni. My topic of research is diffusion in nickel-based superalloys. So this is a second lecture video. It is based on completely an iron carbide phase diagram. So first of all, we will learn interesting topic of material science and engineering. This is a fundamental phase diagram that has been used in complete material metallurgist. So we have to clear about so many concepts in this phase diagram. So we will start as usual. So we will start with an overview of this lecture. That is, so we will start with an introduction to the phase diagram. So what it has two words, that is phase as well as diagram. And second topic is iron iron carbide phase diagram. So iron carbide formula is Fe3C. Second topic is iron carbide phase diagram. And third topic is the reactions, that is invariant reactions that has been coming in this phase diagram. So we will know what is invariant reactions. It's a special kind of a reaction that has been already present in the this phase diagram. After this we will get into the ferrous classification of a ferrous alloys. This is ferrous. Ferrous means iron which consisting of carbon. And second, we will get into the we will jump over the microstructure development of Eutectoid composition. So in detail we will learn what is Eutectoid, what is Eutectic, what is peritectic reactions. Everything we will learn in this video lecture. So what is this Eutectoid composition? What is the special thing of this Eutectic composition? We will know in this complete video lecture. So as I said, this is a phase diagram. Phase diagram. It's consisting of a word called phase. So what is phase? Can anyone tell? So it's an online video. You can comment it in the comment box sections. What is phase? Even though I will tell the clear definition of the phase. Phase is a chemically and physically uniform or a homogeneous quantity of a matter that can be separated mechanically from the non-homogeneous mixtures. It consisting of single or a mixture of a substances. That means if have a substances, we have a homogeneous mixture of a single substance or consisting of single substance or mixture of two substances which is having the same physical property first of all and same chemical property. It's a uniform throughout this area. When you are getting into the next area, this is this area, it's having a different, it may have different physical or chemical compositions which differs the mechanical properties. So that means it's having different mechanical property and this is having a different mechanical property. This is one phase and this is another phase. This is called as a phase. So next, there is a one more word for this phase diagram, that is called as equilibrium diagram. It's also called as diagram. So why it is called as an equilibrium diagram? Before the getting into that one, so what is equilibrium? Equilibrium can be explained with a term of a thermodynamics quantity called as a free energy. Equilibrium diagram. So what do you mean by this equilibrium? So it can be explained with a thermodynamic quantity called as free energy. Free energy. A system. So how? So we can explain this quantity with the help of to explain this free energy. That is, a system is at equilibrium if its free energy is at minimum under some specified combinations of parameters such as temperature, pressure, and compositions. So it should be minimum. It should be minimum value, which can be explained in terms of some parameters such as temperature, pressure, and composition. So in detail, we will learn these things in thermodynamics of materials. So how these phase diagrams, actually these phase diagrams are derived from this free energy diagrams only, free energy concept only. That is with the graph which is plotted between G and G versus X. It looks like kind of these things. So this is G, this is X I, and this is a phase having. So this graph will be explained in the next upcoming lecture video, that is on thermodynamics of materials. So from these diagrams we are getting these phase diagrams actually. So we in reality we are thinking that these are obtained from this. So it's not the case actually. So we are getting at each temperature, we are drawing free energy versus composition, and we are plotting these graphs. From here we are plotting these diagrams at each temperature. So this will be explained in detail in the further lectures. Okay. Yes. As I explained, so phase diagram is plotted between two parameters such as temperature versus pressure, pressure compositions versus temperature, or here good example is pressure versus temperature. It is plotted for water, pure water. So this is a good example and the basic example of a unary phase diagram. So first of all, it consisting of pressure in atmosphere, in y-axis. In x-axis it's consisting of temperature in a degree Celsius, and it's explaining every each phase. If we vary the pressure, so how this temperature is varying the temperature, what are the different phases that we will come across. For example, consider this 1 atmospheric pressure. At 1 atmospheric pressure, at point B, we are having ice is melting at 0 degrees Celsius. This is a melting point of ice. From there, if we are moving, it is a liquid state. As we know that as we increase the temperature, it starts in a liquid state. So it's convert into gaseous state, that we know that this is a boiling point, that is 100 degrees Celsius. Of 100 degrees Celsius, there is a boiling point of water. It will convert its phase from liquid to gases. This is a temperature. There is a 100 degrees Celsius. So afterwards, this point A is called as a triple point. That means all the three phases exist. That is solid, liquid, and gas. All the three phases exist at this pressure and temperature. Solid, solid, liquid plus gas. Triple point. This can be obtained. So at what temperature and pressure the triple point will exist? This can be obtained from this phase diagram. Okay. So now, after completing the introduction to the phase diagram, so we will get into the next important and very interesting topic of this lecture is iron carbide phase diagram. So in this heading, we know this phase diagram in the from the previous slide. This iron, this is a pure iron, that is Fe, and iron carbide, as I mentioned in the previous slide, Fe3C is a Fe3C is iron carbide. So here in this x-axis is having composition of carbon and y-axis is having temperature in degree Celsius. This is very important. So as you seen that composition of carbon is increasing from 0 to only 6.67. So can anyone tell in the comment box that why it is not 200% of carbon is not there? So please comment in the comment section. So I will tell you this answer in the next video lecture. Okay? Yes. So we will start here in this phase diagram. There is only the 6.67 is a maximum percentage of the carbon that is present in the this phase diagram. Okay, this total phase diagram, iron 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 carbon phase diagram is divided into two parts. That is a this is called as iron rich phase, and the another phase which is it varies from 0 to 6.670 weight percent of carbon. So one more is called as graphite region, varies from 6.67 to 100% of carbon. So these are the two phases divided. But in this video lecture, we are learning about only this part, not this part. Okay. So iron rich phase we are learning in this video lecture. That is varying from 0 to 6.67. Okay. Yes. This let's go. So we will start from pure side. Pure side of iron. Pure form of the iron. So we are just increasing the temperature. Okay. So 400 degrees Celsius, we are just increasing the temperature with a 0% of a carbon. There we can see allotropic forms of iron, that is ferrite, austenite and delta ferrite. So when we heat a sample up to 920 degrees Celsius, it's showing alpha ferrite. There it will shows a polymorphic transformation. It forms an austenite. Up to what temperature? Here it is showing 1394. From there to 1538 degrees Celsius, it's showing delta ferrite. So above this one, it's a liquid state. That means it's totally melting. This is the allotropic forms of iron. We will in detail we will learn in the future classes. Sorry, future slides. So it is having alpha ferrite is having BCC structure, whereas austenite is having FCC structure, and delta ferrite is having again BCC structure. So in this, while explaining, just few seconds before, I have used the word called as polymorphic transformation. So what is this polymorphic transformation? So when we heat the sample, there is a rearrangement of the atom so that its form is changed from BCC to FCC, from FCC to BCC. Its a form is changed, structure is changed. This is called as a polymorphic transformation. So I think you guys heard about two words, that is steel and cast iron. So these two are lies in this phase diagram only. We are playing or getting a concept of getting information about these two very basic fundamental material of material science and engineering. We are getting all the information in this phase diagram only. So because of this is a very fundamental phase diagram. So its carbon concentration varies from 0 to 6.67. So only varying from 0 to 6.67 or 6.7 weight percent. So we can get a wide variety of materials such as steel, cast iron, white. So other than this carbon, along with this composition, if we add some other alloying elements, we can get a malleable iron, nodular iron, everything. So we will We will get it that one. So carbon, when we add a carbon to the iron, it will get into the interstitial sites and it will form an interstitial solid solution along with this alpha, astronaut as well as delta. So I have used this word interstitial. So I have used the word called as an interstitial. So there are two things: interstitial and substitutional. Solid solution. So in detail, we will learn in the future videos if possible. So interstitial means this is an atomic arrangements, regular atomic arrangements. This is a solute. It will get into the interstitial site of an atom. So whereas a substitution means so atom will replace host atom. This is called substitutional. Okay, this is the main difference. Or otherwise, you can refer Callister book, Material Science and Engineering. So there it explained very nicely concept of interstitial and substitution solid solution. Okay, so we are learning about allotropic forms of iron. As I said, this is alpha ferrite. Sorry, alpha ferrite, austenite, and delta ferrite. So first of all, we will get into one by one. That is alpha ferrite. This is a microstructure of an alpha ferrite. These are grains of alpha ferrite. So from this phase diagram, it's clearly indicating that the maximum solubility is only 0.0222. So 0.02. It's very less quantity, right? Yes. So what's the reason? It's having this much less quantity. Alpha ferrite is only consumes 0.02 of maximum of 0.02. That to temperature of 727 degrees Celsius. It's too high. So what's the reason? Reason is it's a structure, that is BCC. So BCC can take only this much quantity of carbon. So interstitial sites are not available, not that much available for consuming more amount of carbon. Because of this reason, it consumes very less quantity. And its density, for your information, density is 7.88 grams per centimeter cube. It's from mechanical perspectives, it's a very soft material comparatively, and ductile. Soft means that means it's a ductile in nature. This is a basic information about the alpha ferrite. This is one of the allotropic form. So next is austenite. very famous and interesting topic. So alpha ferrite microstructure looks like this. It's also called as a gamma phase. These are the austenitic grains. So here in these diagrams, purposely I have taken this is a twin boundary. Diagrams are showing. So anyone can answer in the comment box what is called as twin boundary. So what's the difference between this boundary and this normal grain boundaries? So anyone can explain this one. So I will take this grain boundaries in the next lectures, upcoming lectures. Okay. This austenite, it's having solubility of up to 2.14. That to temperature, very high temperature. It's about 1147 degrees Celsius. It varies according to book. So this alpha ferrite is having very less quantity 0.00 but it's 100 times greater than that of the alpha ferrite. Also it consumes 2.14% of the carbon. So what's the reason? Same, this is FCC. Because of this structure, it can eat more amount of carbon than this BCC. But so next is remaining last but not least. So this is delta ferrite. As the name indicates, it's a ferrite structure, that is BCC, similar to that of the alpha ferrite. Its main difference is presence of temperature. It's a delta ferrite is stable at high temperature and alpha ferrite is stable at low temperature. So we will see the microstructure. So this is a microstructure of delta ferrite. So this is sorry. So this is delta ferrite, which is distributed in the austenite. This is a microstructure of delta ferrite. So due to its high temperature, delta ferrite is not yet explored completely comparatively other two allotropic forms of iron. So this is allotropic form. Now we have covered. Next is other side, opposite side of phase diagram, that is Semantic Region. It's having a composition of 6.70. From the phase diagram it is clearly indicating from 0 to room temperature to 7 degrees Celsius. It is having, it exists along with alpha ferrite from 7 to 7 degrees Celsius to 1147 degrees Celsius. It exists with gamma. This is called ledeborite. This is called perlite. So above this one, here it is liquid plus comma liquid plus vaporite it's having. So here it is completely above this temperature, it is completely liquid state. So as we know that this cemented is intermetallic compound having more brittle property comparatively other uh, comparatively iron, pure form of the iron. So presence of this cementite, so strength of the mechanical properties of iron has been increased. This is a key word. So one more interesting fact about the cementite is it's not an equilibrium phase. It's a metastable state. So Fe3C is not equilibrium state. It's a metastable state. So hence this Fe3C called, it's not called, it's not a true, it's not a true equilibrium diagram. So when we heat the sample, for example, when we heat this intermetallic cementite from one particular temperature, it will be in this state only, cementite only, for longer duration of time. So hence it is called as it's a stable for long duration of time. This is all about the allotropic form, that is a single phase field of iron carbide phase diagram. So we will get into the reactions present in this phase diagram, that is called as invariant reactions. These are called as an invariant reactions. So there is a special name called invariant. So what's the reason? We have to think in this way. So we have to ask ourselves why it is called as normal chemical reactions. So why it is called as an invariant reactions? There is one reason. There is a given a one formula called as P plus F is equals to C plus 2. So P means phase, F means degrees of freedom, and C means chemical compositions. So 2 is a parameters that we are using here, pressure plus temperatures. To plot this phase diagrams, we are keeping pressure as a constant term and we are varying only temperature versus composition. Hence, this formula can be reduced into P plus F is equals to C plus 2. Most of the people will get confused why will be the 1, why it's not 2, how it is reduced into 2 from 2 to 1. This is the main reason. We are keeping the pressure as constant. Okay, so that's why one term has been reduced. So invariant, in simple words, invariant means degrees of freedom is 0. That is, here F will be the 0. So by saying degrees of freedom will be 0, that means what? So what it indicates? What is the special thing about this one? So this can be observed from phase diagram. Okay. Yes. So invent. This is the invariant reactions. As I mentioned in the slide, uh, there are three invariant reactions. Here it is one, and here it is one more, and third is here. This is called Eutectoid reaction. Here it is Eutectic reaction, and third is Peritectic reaction. So to get this point, single point, this point, this point, and this point, we are keeping temperature and as well as composition constant. So we are getting this only one single point is there here. So at particular composition, at particular temperature, we are getting this reaction. So because of this, both are constant, both parameters. Here the two parameters are varying. Here temperature is varying. Here composition is varying. But to get this reaction, we are keeping both the parameters are constant. There is no freedom at all. So if you move away, little bit away from here, or little bit here, or if we increase the temperature here or decrease the temperature here, we won't get this reaction. Because of this reason, this is called as an invariant reaction. Okay, so as I introduced, we will learn one by one reaction. First is eutectic. This can be obtained with the liquid can be changed into two solids, that is gamma plus Fe3C, that is cementite. Both are called as lead-brite. So this is a eutectic reaction. Whereas eutectoid reaction, it can be obtained, that is one solid is transformed into two solids. Here liquid is transformed into solid 1 plus solid 2. So whereas peritectic reaction can be transformed into one solid plus liquid transformed into one solid. It is delta plus liquid transformed into gamma astronauts. This is peritectic reaction. These are called as invariant reactions present in this phase diagrams. So I think you are clear about why it is called as an invariant reactions, right? Here I will write once again for your clear eutectic reaction. There is liquid. So, liquid will change into two solids, solid 1 plus solid 2. So Eutectoid is converted into solid is converted into solid 1 plus solid 2. Peritectic is liquid plus solid will convert into one more solid. This is the basic definitions or reactions of invariant reactions. These three are present in this. So many. Other than this one, there is one more reaction. Is a peritectoid reaction. Is a eutectoid. So as we mentioned, peritectoid is also there. So we will. It's there in the other phase diagrams. Okay. Okay. So we will have now classification of ferrosols. Classification. So there are three classification. That is pure iron form. There is a ferrite form. Here it is there, which is having 0% of carbon. Second is steel. Very interesting topic of material science and engineering. So it's a wide variety of application is there. And third is a cast iron. This is also very interesting, and most researcher worked on this in cast iron. In this steel, again it is divided into two forms. That is hypo-eutectoid steel and hyper-eutectoid steel and eutectoid steel. Three are there. These three steels are there. So this iron in pure iron, if it is that is pure iron, carbon concentration if it is less than 0.008 weight percent of carbon, and steel is having 0.0082 to 2.14 weight percent of carbon. For cast iron, so it's 2.14 to 6.70 weight percent of carbon. This is the weight percent. Okay. So how is this microstructure? Microstructure will varies. Okay. As I said this for pure iron, I have shown you the microstructure. So that is a grains that is there in this slide. This is a pure iron, almost pure iron form. This is having grains of alpha ferrite. Okay, sorry. This one. Whereas a steel is having paralytic region. That is alpha ferrite plus cementite. Alpha ferrite plus cementite. The hypoeutectoid is having perlite plus ferrite, whereas hypereutectoid is having perlite plus cementite. But eutectoid steel is having only perlite equation. So from astronite, when we are getting into this steel, that is eutectoid steel, we are getting an alternate layer. There is a alpha plus cementite. So what's the reason? How this microstructure has been evolved? So this area of this area and this area we will learn in the upcoming classes. This is called as pro-eutectoid alpha. Here it is that when we are moving from austenite to this one, we are getting perlite plus pro-eutectoid alpha. Here it is having perlite plus pro-eutectoid cementite. So what's the reason? Only the small variation in this composition, we are getting totally two different microstructures with the two different mechanical properties. So what's the reason? Before that one, we have to sort out these things. At Eutectoid, we are getting alternate layer of alpha plus Fe3C. That is, this is called as a perlite. So how this microstructure is evolved? There is an next slide. This is a development of a microstructure. Development of a microstructure at Eutectoid composition. It should be Eutectoid composition. Sorry, at Eutectoid composition. So first of all, we will keep the sample here in the gamma at this temperature, and we are moving from this x to x dash region. So we are placing a different 2 points A and B. So we are seeing the two microstructures. What's the difference? So as we know that at eutectoid composition, that means it's a composition of 0.76, right? Yes, 77 weight percent. Carbon is called as a eutectoid composition. So at point A, it's completely austenitic region at this temperature, that is 800 degrees Celsius. So when we are cooling down the sample, so it's austenite only. So when this temperature 7 to 7 degrees Celsius, this is Jadu temperature. When just it will causes this temperature, it started forming alternate layer of alpha and Fe3C. From gamma. This is called, that's called a Eutectoid reaction. Okay, so one solid is giving to two different solids. It started forming alpha plus Fe3C. But before this one, only a single grain is there. When we are reducing the temperature, after crossing this 7 to 7 degrees Celsius, it is formed as alternate layer of alpha and Fe3C. This is a bright and dark regions are there actually. Okay, this is all about today's lecture, and this is starting of evolution of microstructure in the iron carbide diagram. Okay, so in next video lecture, so we will know about how these two phases are formed. Alpha plus Fe3C is formed. What is the mechanism? Second is hypo and hyper Eutectoid reactions. So how this microstructure is evolved. As in the previous few minutes before, I said I have used pro-eutectoid alpha ferrite and pro-eutectoid cementite. They are formed. So how they are formed, why they are formed. So we will know about those things in the upcoming lectures. That is the next lecture.